We're going to go through an exercise on rain garden design. I'm taking this from the North Carolina Best Management Practice Manual, and we're going to design a bioretention cell, a rain garden, to take the runoff from an 80-foot by 100-foot parking lot. We're going to design for 1 inch of rainfall. So we're going to run it from the parking lot into this engineered facility. So it's not just a pond, it's not just a garden, it's an engineered facility. We have a size pond here, and then we have under media there, the soil media. We have some details on that. There's a couple of different layers of that. We do have an under drain. In this case, it's going to take it out after it goes through that, and then we have to have an overflow structure for very high flows. It's not designed to take huge storms. It's designed to capture most storms and run it through the ground like that. All right. And again, we're going to run it onto this rain garden from a parking lot. Parking lot is 80 foot by 100 feet. We're going to design for a 1 inch rainfall. Pond depth, it says 9 to 12 inches up there. We're going to design it for 9 inches or 3/4 of a foot. Depth of the soil is 3 feet. Now you'll find some guidance given different numbers on suggestions for that. We're going to do ours with 3 feet, which includes 0.5 feet of surface soil, then 2 feet of mixed sand, and then 0.5 feet of wash sand underneath that. And the hydraulic conductivities of those media are given. Porosity of soil, we'll need that for volume calculations, is 0.3. And the slope of the under drain pipe is 0.5%. All right, so first thing we're going to do is calculate the runoff from a 1 inch storm. Now we could, in some guidelines they might say, like the simplified method, just treat 1 inch of runoff. But here we're going to do a 1 inch storm and calculate the runoff using the curve number method, which we know well by now. So impermeable is going to be a 98 curve number, and then from that we calculate the storage, 204 inches, and then our Q is the runoff. We plug in our numbers in and we get 0.79 inches. So then the volume of runoff is the area, which was what, 80 feet by 100 feet? Times the runoff of 0.79 inches. Take that times 1 foot per 12 inch, and we get 527 cubic feet. So first thing we need to figure out is now we want that 527 cubic feet to be ponded there. So we're not going to assume any immediately infiltrates. It's going to be ponded there, and then it's going to infiltrate over time. So we want that pond to be able to hold that volume. So then the area that pond needs to be is the 527 cubic feet it needs to hold, divided by the depth of the pond of 9 inches or 0.75 feet. Again, that's 9 inches. And that's 703 square feet. So it's 9 inches deep, and then it's going to be 703 square feet in area. So let's make it about, so we want to have a nice pond shape, and we're going to work with our existing property there to kind of put the pond where we want it. But for simplicity, let's just make this 35 feet by 20 feet. So it's actually 700 square feet, close enough. So maybe make it like 20 this way and 35 this way. So that's what we're going to do for the pond size. And again, we're running the water off from a parking lot there. How it gets there, and I've seen a number of these. There's different, some of them actually have a little culvert running from the parking lot to the rain garden. It's better if we can run it over the land, sheet flow, and we have some grass around it, so it runs over that overland in there. All right, so let's calculate the time it takes to draw down. So this one, the pond must drain in less than 12 hours. We want to know how fast it's going. So I'm going to use something called the harmonic mean, which at one point in my life I thought I invented, but it's been around for thousands of years. The harmonic mean is used for things in series. So if you're taking a trip and you go 10 miles at 100 miles an hour and 10 miles at 1 mile an hour, well, 100 plus 1 is 101 divided by 2. You average 50.5 miles per hour. No, you don't. It's going to take you 100 hours to go that 100 miles at 1 mile an hour. So that's going to control what you do. So if we're going vertically, so our engineered system, we have these layers, and in general, groundwater tends to be deposited in layers. And the water has to go down through there. So if one of these layers is slower than the others, it's going to take a lot of time to go through one of the slow layers. It's slow down. So if I do some algebra on that, again, I did this and thought I invented it until I figured out it was something with a name that's been around forever. It's something called the harmonic mean, and there's the equation for it, but it turns out so. Okay, L1 harmonic mean equals L1 plus L. What's L? Okay, so this layer is 0.5 feet. This layer is 2 feet. This layer is also 0.5 feet. The K hydraulic conductivity of this layer is 0.2. I think it's inches per hour. You can't read that, but you can look up above and see the numbers. K2 is 2.4 inches per hour, and K3 is 12 inches per hour. So our harmonic mean, to calculate the time, velocity based on the time it takes to go through this layer, then this layer, then this layer, is the sum of the L's, so that's 3 feet. 3 feet. L1 plus L2 plus L3 is 3 feet. 0.5 plus 2 plus 0.5 over, on the bottom here we have L1 of 0.5 feet divided by its K of 0.2 inches per hour plus the second layer, 2 feet, put 2.0, divided by 2.4 inches per hour plus 0.5 feet divided by 12 inches per hour. And that turns out to be, I kind of got in the way with my arrow there. That turns out to be 0.89 inches per hour. That's my arrow there. Okay. That's a little fun thing I like to point out, but with groundwater. All right, so let's calculate Q. This Q is the flow. So we have the Q of the SCS method, which is really not a flow, it's inches of runoff. So we'll use Darcy's law. Darcy's law, the little q or v, whatever we want to call, different references call different things, like we said, because the flow over the area is k times dH dl, or the change in head with the distance. If the under drain is fast, that means that the water down here is going to be taken away real fast, so we don't really have any pressure head there. It's taken away. So I'm going to say that when the water drops 3 feet, the head decreases 3 feet. So I'm going to say that the hydraulic gradient is 1 foot per foot, or inch per inch. So the Darcy's law then says Q over A equals K dH dL. So really, remember we always say we want to have a negative in there. So it's good 0.89 inches per hour times 1 inch per inch equals 0.89 inches per hour. And if I want to be rigorous, I put a negative sign there, and this is actually minus 1 inch per hour times minus 1. Alright, so that's Q divided by the area. So then the flow of water down through then is the Q divided by A, 0.89 inches per hour, times the area. Remember, our area is 7 of our ground surface that's going down through is 700 square feet. We got inches there, feet's there. How about take that times 1 foot per 12 inch equals 52 cubic feet per hour. By the way, that's 6.5 gallons per minute. Alright, so the time to drain pond, we're going to do the volume of the pond is 525, remember that, cubic feet. The water is now draining down, heading down at 52 cubic feet per hour. That's what we just did right there. This is how fast it's draining. So its volume is 525 cubic feet divided by 52 feet cubed per hour equals right about 10 hours. Remember, we said we need to drain it in less than 12 hours. So we got that. That's good. Alright, so it's time to drain the pond down to the bottom of the pond. We got another requirement that we need to drain from the surface down to 2 feet below the surface. So the volume in that, alright, so go back up here. We made some simplifying assumptions, and we said that we have 527, or actually 525, it turns out to be, cubic feet in here in this ponding area. Now we're going to have to drain it down through there. Once it gets to the water surface is right there, we're going to have to let it drain down. And so the volume below that now includes the soil, so we've got to count for that. So then our volume of 2 feet of depth of our subsurface is 2 feet times 700 square feet in area. What was the 520? No, 525 was the volume of the pond, which was 700 feet squared times 0.75 feet, or 3/4 of a foot deep. The area of it is 700 square feet, and then the porosity of 0.3. So the void area, the area available for the water, is the 2 feet of depth times the 700 square foot area times the porosity of 0.3, and that gives me 420 cubic feet. So then the time to drain, I probably should have left more room here. The time to drain is 420 cubic feet that we need to drain. And maybe after I write this, I'll adjust it for you all. Make this another step. 420 cubic feet drained divided by our rate of 52 cubic feet per hour is 8.1 hours. So then the total time to drain down from the top surface down to the bottom of the pond and then 2 feet below the pond is the 10 hours it took to drain the pond plus the 8 hours it took to drain down 2 feet below, equals 18 hours. And that's less than 24 hours that this was required to be. So we're good there. By the way, these calculations, you could have just said the time to drain the pond is the depth, remember the flow divided by the total area, 9 inches divided by 0.89 inch per hour, 10 hours, and then once you get below the surface, and then in the soil we have the porosity, we have the soil in the way, so we have to use the V. Seepage, which remember is Q, which is big Q over A, this is the specific discharge divided by N, the porosity, or 0.89 inch per hour over 0.3, porosity equals 2.9 inch per hour. So I could have just said it's 2 feet going down, and it's going down at a rate of 2.9 inch per hour times 12 inches per foot is 8.1 hours for through the soil. So whichever way you want to look at it, might be easier to think of it as a flow going down through, or you might think in terms of the specific discharge and the seepage velocity. All right, now that's kind of the main part I want to go. We do also need to size the pipe, the underdrain pipe. So I could use Manning's equation, for example, and say I want to put in there a 4-inch pipe at going at 0.005 slope. If I use my Manning's equation or use the nomograph, which is actually attached at the end of this, it's turns out to be 65 gallons per minute capacity for a 4-inch pipe at a slope of 0.005. Yeah, I think we had I think we said we need to drain, our drainage rate is 6.5 gallons per minute coming down through there. So we're 10 times above that. And if I go to a 6-inch pipe, that's something on the order of about like 180 gallons per minute. So the pipe is not the issue. And then I won't go into it for sake of time. We also need to remember we have an overflow system and we need to size that. And we can do that according to general retention pond design, but I won't go into that. We could use a Weir equation or some other equations to size that. I want to wind it up by talking about a few things. We could do, and we can do the same thing with retention ponds, a more detailed method, a hydrograph time step simulation. We could also do a simpler method where we don't do our harmonic average of the K values, and some of the things so a rain garden handles volume by getting it to infiltrate. It also this is often the main reason is to use it for water quality. For total suspended solids, if we have any soil there that is running through, we get the solids out. Metals and phosphorus get out. Those are dissolved, so they will get out through some reaction or absorption to the material, and you need at least a foot of material for that to go through. For nitrogen, I saw somewhere it's 30 inches. Now nitrate is dissolved and not reacts with anything, so I'm not sure the nitrate would make it through, but other than nitrogen, I guess. Fecocoliform, like the solids, it gets physically filtered out, so you don't have, if you're putting it through the soil, you're going to get that. Temperature, so that's another reason to use it, is that water running off a hot parking lot can have a big impact on the temperature in the stream, which will affect aquatic life and fish. So another reason to run it down through the ground is to reduce the temperature, and they suggest 3 feet of depth for that. Under drain, so this one we mentioned an under drain system. It could be that you're on a native soil that is permeable enough that you don't necessarily need that under drain system. So that kind of depends on the soil. Vegetation choices are crucial. If you look at some guidelines for rain gardens, there's been a whole lot about the vegetation and what can work. So we use native plants, but that's a critical step in it. All right, so that's a little run through of a design of a specific type of best management practice, and we'll move on from there.